Welcome back, scholars. This is the third video in our series all about functions. This time we'll start looking at some of the most common parent function families as well as ways of describing specific features on the graph. Let's get started. The first function you studied was a linear function. While you are likely most familiar with the equation for a linear function written in slope-intercept form, it's useful to be able to use both standard form and point-slope forms just as fluently. Linear functions, of course, are known for their constant rate of change, also known as slope. This parameter is often given the designation of m in American textbooks. It's sometimes called the gradient of a line and may be shown with a different letter coefficient, such as a. The y-intercept is the constant which is added or subtracted to the variable term in the equation. In point-slope form, the y and the x remain in their variable form, but an ordered pair takes the place of x sub 1 and y sub 1 in the equation along with the slope. There are two special cases of linear functions. The first would take the form of y equals some constant. This is called the constant function, and the slope in this case is 0. You may also see y equals x referred to as the identity function. In this case, the slope is 1 and the y-intercept is 0. This is also the parent linear function. Polynomial functions took up a substantial amount of time in your algebra course last year. A polynomial function is one where our variable term or terms are raised to a constant power. The exponent must be a positive integer, so no fractional exponents and no negative exponents. The degree of a polynomial is the highest power of any term in the polynomial. Written in standard form, we write the highest degree term first. Its coefficient is referred to as the leading coefficient of the function. Starting on the left here, I have a third degree polynomial whose parent function will be the cubic function y equals x to the third. I can see from the graph that there is one real root, which shows up as an x-intercept on the negative x-axis. Since this is a third degree polynomial, there must be 3 roots, so the remaining 2 roots must be a conjugate pair of imaginary roots. Note that imaginary and irrational roots only appear in conjugate pairs. Next, I notice the end behavior of the function is mismatched on the left and right-hand sides. Note that as x goes to infinity, y goes to positive infinity. As x goes to negative infinity, y also goes to negative infinity. The end behavior would be reversed on the left and right-hand sides if the leading coefficient of the polynomial was negative. In the middle, I have a 4th degree polynomial whose parent function is the quartic function y equals x to the 4th. This time, I see a total of 4 real roots that show up as x-intercepts. Since this is a 4th degree polynomial, there are exactly 4 roots, and all 4 of those roots are accounted for as x-intercepts, so there are no imaginary roots this time. Next, let's take a quick look at the end behavior, which fits the even degree polynomial pattern. Notice how the end behavior matches on the left and right-hand sides. Just like a parabola with a positive leading coefficient, this even degree function opens upward on the left and right-hand sides. If the leading coefficient were negative, this polynomial would open downward. Last, on the right, we have a 5th degree polynomial. The parent function will be y equals x to the 5th. We see that odd degree end behavior, and we see one real root through the origin. Since this is a 5th degree polynomial, there must be a total of 5 roots, so the remaining 4 roots must be imaginary. Actually, that will be 2 pairs of imaginary roots. We'll take a quick look at radical functions as well, specifically the square root function, which has an index of 2, and the cube root function, which has the odd index of 3. All even index functions will take the general appearance of the square root function, while odd index functions will be a variation on the cube root function. The key difference to think about algebraically here are the domain and ranges for each function. For the square root or even index roots, we will not have a real number output with a negative radicand. That is the value underneath the radical, so we'll need to restrict our domain accordingly. For the square root function, we have 0 to infinity for both our domain and our range. Now, keep in mind that we can indeed reflect or translate this function to place it in quadrants other than quadrant 1. So this is just a starting point, but it won't be the domain and range for every possible square root function. For the cube root function and other odd index roots, we can indeed have a negative radicand with a real number result. So our domain is unrestricted and will include all real numbers for the domain and also for the range. Last but not least, please remember that a radical is an alternative symbol to using rational or fractional exponents, where the denominator of the exponent is the index of the radical. We'll spend a whole lesson reviewing rational functions because there's lots of details to see and recall, but we'll briefly point out the essentials for finding domain and range. The rational function is composed of a ratio of two polynomial functions, the simplest of which is the reciprocal function 1 over x. With rational functions, our primary concern is excluding any values that can cause the denominator to equal 0. This leads to an undefined result and shows up on the graph as a discontinuity, either as a vertical asymptote or potentially as a hole. We see evidence of such discontinuities in both of the examples here. With the reciprocal function, we need to exclude the value 0 from the domain. This shows up as a vertical asymptote located at x equals 0. With the example on the right, we exclude two values, both at positive and negative 2. This means that our denominator must be the difference of two squares, x squared minus 4, which factors to x plus 2 times x minus 2. So far, we've looked exclusively at what are collectively referred to as algebraic functions. These are functions that are constructed entirely from basic operations such as addition, subtraction, multiplication, and division. The alternative is that a function could be classified as transcendental. This would be exponential, logarithmic, and even trigonometric functions, which cannot be expressed as a finite number of algebraic operations. Last, let's review how we might describe the appearance or behavior of functions beyond just domain and range. We use interval notation to describe other sections of interest in our function. For example, we might describe an interval where a function is increasing or decreasing. By convention, we refer to these intervals using inputs or x values, and we use what are called open intervals, which means that we use parentheses and do not include endpoints. The parabola pictured is increasing for all inputs from negative infinity until we reach the vertex at x equals 0. Then the function is decreasing from 0 to positive infinity. The function is neither increasing nor decreasing at its highest point, so we do not include x equals 0 in either interval. Intervals of positivity or negativity work in a similar fashion. These are inputs for which our outputs are positive, meaning greater than 0, or negative, meaning less than 0. For our example function, we see that the outputs are negative or below the x-axis for two intervals, from negative infinity up until x equals negative 2, and then again from positive 2 until positive infinity. By contrast, the outputs are positive, meaning above the x-axis, between the two negative intervals, from negative 2 all the way until we reach positive 2. Again, when the function's output equals 0, we are neither positive nor negative, so we do not include endpoints with these open intervals. That wraps up our look at some parent functions and their features. Next time, we'll look at transcendental functions and some special functions like piecewise and step functions. See you then.